we're rolling. Okay. Sorry, I was in the back panicking. I need to figure out why this wasn't displaying. There's a right combination of buttons to press. Hi. You may have noticed that I managed just before class started to actually post everybody's grades for the midterm. This is where everybody whips out their various devices and checks their grade. As I'm talking about it, however, and you might have so I tried to put a piece of feedback in there. This is true for everyone. If you don't like the number that is there and you'd like to improve it and you suspect that some of the multiple choice questions were wrong, you can come and retrieve your midterm and you can do the following two things. For every multiple choice question that you got wrong, you say, this is what I thought, this is why it's wrong, and here's the correct answer. Right? So those three steps. If you give that back to me, that's worth half the points still. So this need not be your final grade, especially if it's sort of flagged yours like, okay, I think we can do better here, we can do better, okay? I was the part of the, if you've got like 70 or 80 and you're like, you know what, I would like to bump this. That's what I'm thinking. Most of you did really well, thank you very much. So I think we can move on. The level of anxiety is lowering as we speak. There are a couple of people that need to do a makeup exam, so we'll set a makeup day for that in the near future to get the last 8 people to do a midterm. Any questions about your midterm grade as you've all checked it and not heard the word I said? Everybody happy with the grade? If you're not happy with the grade, come talk to me. We can do the whole makeup points thing. All right. Fantastic. So, life of stars, we're now going to talk about actual astrophysics. So we've talked about the physics component of this, like we did gravity, we did light, we did scales, we did distances, we figured out how we did the distances, and so now we're completely equipped to do this. If you're flagged, I wanted to make sure that this was in here. Flagging is not failing, it's basically us checking in. And so if you have been flagged, this was basically me saying like, oh, I haven't seen like group work from this person. Can they get to class? Is their car broken? You know, somebody check. So that's how we do it, right? And so this is if you do the homeworks, if you do the group works, if you do the pre-class works, you know, you can see your final grade sort of scale accordingly. So that was the other part of it, right? If you've been flagged, or if I said a comment on it in your grade, not many, but if you, hey, not the end of the world, let's address it now, all right? Cool, so how heat gets around. This is important, this has been important the last month, hasn't it, right? Like, you've all felt the draft, you've all felt the little space heater sort of glow in the corner. And so this tells us about a couple of ways that heat can be transported, right? So we basically have 3 ways that heat can go from one end of the room to the other. You can have radiation, so you can literally feel the glow, right? So maybe it actually has like one of these old school heating elements. Who has one of those? You have like a space heater that you can actually see the glow start like, yeah. Terrify me every time I see one of those, but all right. So that works mostly on radiation, but the hot element also starts making air circulate, right? So the hot air rises, and so you get a circulation of air, and you can have conduction. That's really when you touch the heating element, not recommended, right? But you can have a way that you, for example, sitting next to, you can sit next to a fire, but also, for example, you feel that the floor warms up. The slides will be available as per usual. Sorry, because I was finicking with the projector, I haven't actually put the slides on, sorry. And so these are the 3 ways that we can get heat from one part to the other. You can feel that, for example, if you put your hand on the car, your hand gets cold really, really fast, because metal is a fantastic heat conductor, so the heat goes out of your hand into the metal and spreads out of your car. So that's why stuff feels cold. Stuff doesn't feel cold if it's like a bad heat conductor, like your woolen sweater, for example. That keeps you nice and warm because it doesn't conduct heat very well. So, how How does it work in stars? Exactly the same way, right? So how to get the heat from the center of the sun to the outer parts of the sun uses the same three processes, just at really much hotter temperatures, and they're not equally important at different layers of the sun. Because if you want to have convection, you know, you have to have a freely moving medium, right? So for example, your car engine is cooled by what's essentially forced convection, right? You have a cooling medium, you have a cooling. Am I the only person who looked under the hood of that car to wonder where the sound came from? All right, so it's like you look at that and there's a whole cooling system, right? So that's forced convection, right? You stick something, it absorbs some heat, and you move that something away. That works in some parts of the sun, but if it's just too stiff or too dense to move, then you can't have convection, for example. And so when you look at the sun, there is a convective zone because that's where the density gets low enough that you can actually have some of the stuff move. And so when you see things like the dark spots, the sunspots, that is partly because there's a convective cell underneath that's moving new stuff out from lower down up to the surface. So you have a convective zone on the outside, and on the inside, it is simply too dense for anything to really move. So convection's out, which means that if you want to get heat from the core, where fusion is happening, you want to get it out and further, you can only use radiation, really. So light from the core, radiation from the core, that's how it transports from the inner center to the part where it starts convecting. Once you get to the convecting zone, you can get two or three different ways to get the heat out to the surface. So it takes a while for the heat from the core to get all the way to the surface. It takes a while from, if you produce new energy here in the core, to actually then get radiated away. It's 100,000 years between when the energy here is made from fusion. We'll talk about that next on Thursday, to when you get to the surface of the sun and when it starts radiating away. Once you get to the surface of the sun, once again, like at this point, there's hardly anything there. Where you've got a very thin atmosphere of the sun, called the corona. That's super thin. So maybe some of that stuff gets ejected. So sure, that takes some of the heat with it. But everything else has to be radiated away, otherwise the heat stays. So pretty much exactly like your little space heater, right? Your space heater either heats the air right above it, and so a little bit moves off from that, but most of it needs to be radiated towards the rest of the room. Is the simile okay? Right. So it depends on how dense your star is, how well it manages to get its energy from inside to outside. That convection part is really important because it mixes the outer part of the sun with the lower parts of the sun. So if you're fusing hydrogen at the center, again, we'll get back to that, and for example, you want fresh fuel, if your convection layer goes all the way to the core, then you can literally use fuel from all through the star. But if you're like the sun, there's only so much, there's a convection layer, and then there's basically a part that doesn't move, then you can only use the fuel that's in the core itself already. So some stars live a really long time because they're completely convective, right? The bits from the outside go all the way down to the core and back up. And those are embryos. That's the reason that they're part of the reason that they live so long. So we have these three ways to move energy around. We can do radiation, similar to how you perceive the heat from the heat lamp, just much higher temperature, conduction, same way of metal panels become too hot too, and convection, circulation of material from the core to the cooler surface, exactly like draft, and exactly like most forced air, for example. So remember these two kinds of emission? We had how hot it was, and that's the surface. That's essentially directly related to temperature. I noticed a bunch of people didn't quite remember this one. I gave you the constant, so the maximum wavelength is like that constant divided by the temperature. And so that gives you the length of the wavelength where the peak is. So I thought we check into that. Where that peak is tells you directly what temperature it is. The shorter the wavelength, the peak moves towards the blue, the hotter the star is. We also I'm hotter, I'm moving the top of this, the peak to the left. If I'm cooler, I'm moving to the right. And then I have Stefan's law, that's the total luminosity is how much I'm producing at the surface times the area. So it's the size of the star, but also the temperature. So if I'm making it bigger, I can be the same temperature, but I'm actually putting out way more luminosity. So I can be big or small at the same temperature. And so I can be luminous because I'm both hot, or I can be luminous because I'm big, or I can be luminous because I'm both. Right? So that was the underlying idea. And then from the absorption and emission lines, we can actually see what stars are made of. And so one of the big discoveries for when we looked at spectra from the nearby stars was that, hey, they're mostly made out of hydrogen. And that wasn't really known. And so, for example, the ancient Greeks was like, well, that looks like a giant furnace. Must be a lot of coal. All the way up to the 19th century, somebody figured out that it would take 100,000 years to, if the thing is entirely made out of coal, and that thing is actually burning, it can take 100,000 years to burn through that big of a amount of coal. So, must be something else. But what it was not really known. So we got to hydrogen. That was fairly recent. That we, so beginning of 20th century, that all the stars actually are predominantly made of hydrogen. And so, just to reiterate, hot thing, black body, just a cloudy gas from one element, or maybe a couple elements. You see the emission lines, and if it's a hot thing that shines through a cloudy gas, we get the absorption features as the hot gas, because the gas here basically absorbs that particular wavelength and then radiates it in every direction, so you don't actually see it. So you get a black body and emission lines spectrum versus absorption spectrum. Just to reiterate, like if you put the moon in front, then you get just a corona, but if you look through the corona, then you see those lines. Corona material is the same. The moon again. Yes. All right. Star's colors reveals its surface temperature. What color is the star? It is red, blue, green, or yellow. Just for everyone, everybody woke it up. 2 and 3. Yes, fantastic. All right. What color is this star? 1, 2, 3. Yes, sea of red. And so its color reveals its surface temperature. We've got another one here. And so that first gives you an idea of like how hot that star is. But we got a more sophisticated classification system so the Harvard spectral classification. So at Harvard, there was this group of women called the computers, and they were going over the spectra of each star as it came in, right? So they could actually do this in a warm room inside, because the spectra were coming in as photographs. This is when photography got good, and you didn't have to be a chemist to actually make it work. And so the photography came in, the photographic plates, the glass plates with the photography came in, and they classified spectra. And one of the things that was noticed was that actually an earlier classification system, which was alphabetical, didn't quite work, because they started classifying using these emission lines. And so you have O, B, A, F, G, K, M, and that's really hard to remember. So we need to have a classification mnemonic. And so there's 7 classes. There's a couple added more recently. And so, for example, the sun is a G2, so it's like right here. And so it's classified on how strong those absorption lines are. So basically what kind of material is in there. So if you're an O star, it's a little faint, but this is a hydrogen line. That becomes more prominent in the F stars, and it sort of goes away in the other ones. And they have a strong, I think that's an iron line. And so those are the spectrum that we classify on. And that was done by Cecilia Payne. And she also came up with the mnemonic, which is O be a fine girl, guy, kiss me. And so that's how you can remember the O, B, A, F, G, K, M classification. O being the hottest, but also having the least hydrogen absorption, and then basically going to cooler. And so, I say popular mnemonic, but my issue with this is this, like, unfortunately over the last few years, 3 extra classes have been added, L, T, and Y, because those we only found when we got near infrared cameras. So this is where only the ones that we can actually see. M is the coolest stars that you can actually see. L, T, and Y are not really visible to the naked eye. Can anyone think of a good mnemonic, and so this is an extra credit, for the sequence of letters that isn't mildly creepy? So I've seen some really excellent ones from students in the last few years. Can you come up with a mnemonic that isn't, oh, be a fine girl, kiss me, and then also take these LTY into account, and then we're in business. So I really love what, hit me. Give me your best mnemonic. If you're good with words, please do use this extra credit. Yeah? Okay. All right, so what are they, right? So what is an O star, what is an M star? And so these extra ones are actually substellar or really small stars known as the brown dwarfs. Maybe they're failed stars that are only recently discovered. So for example, it's not this star, it's that little thing here with the Hubble Space Telescope. This is in 1995. With the James Webb Space Telescope, we've been looking at it more and more. We actually launched the WISE satellite to pretty much look for these specifically. And so one of the things that was found, so notice this is Barnard's star, discovered in 1916. This is Proxima Centauri, discovered, one of the Alpha Centauri was basically got a distance in 1839. Proxima Centauri is its companion star, so that was discovered in 1917. And I want you to note the other ones, the other 2 here in our local neighborhood, right? This is the sun, 2 light years, 4 light years. There's Alpha Centauri, the closest star. And then we've got Barnard's star. And then we've got 2 from 2013 and 2014. You wouldn't think that we found some of the nearest stars only a decade ago. I mean, if you walked in and go like, surely they found all the stars near us already in my lifetime, right? Was that a preconception that you walked in with? Or did you think, yeah, I'm sure they're discovering new ones all the time? What did you real think? Oh wow, it still feels like Monday in here. All right, yes?
I got a few years ago, almost the nearest stuff.
Right, you can see them, right? That's the whole feeling. Like you walk in, you look up, like that's where they are. So that should be the nearest ones. Yes? So that's the other part, right? We're getting better detectors. But the near ones, really? So, yeah, those are a little over 6 light years away. And we got very excited about them because they're low mass, very long living, and then also nearby. So how cool would it be to find a rocky planet around one of them, right? Like one actually nearby, literally the neighbors. So these things will be the target, or are the target of James Webb intense campaigns to see if we can find if they have a nearby, if there's actually a planet around. But so this gives you an idea of what the local environment is. So let's see if I can find a couple. Like notice that a couple of them have like very specifically. This is the dude who found them, like 19th century. I'm just naming that star because I managed to actually get it in my photographic plates, and I managed to get a distance. So it's like, yeah, it's within the next 20 or 15 or 30 light years. And so there is Lacaille, Ross, Captain, where we just had another one. If you are a huge Star Trek fan, you've heard of Wolf 359. This is totally grabbed from this because like, oh, it must be close to Earth, right? So like that's one of them. Lagging Star and T-Garden, like these are all the people that basically found the distances. When we talk about distance, they found the parallax, like that star is actually near us. So finding our local neighborhood is a whole process in itself, and really we're only getting a full view from it now. Because this gives you an idea of like how hard it is to find these things. This is just a picture for like set with the contrast all the way up, right? Maybe you've done this where if you've ever played with any kind of image processing, you put a dark image, you dial it all the way up. This is basically the noise from the camera. But that little dot there is one of those nearby brown dwarfs. They saw it move, they saw it have a parallax, and it's like, wait a minute, that's a real source, that's a real star, and it's nearby. There you go, you can see it move ever so slightly. So yes, you have to go rummage in the noise and see for these tiny little dots to move back and forth. So what we've subsequently discovered was O stars are over 30,000 Kelvin in surface temperature. B stars 10,000 to 33,000, A stars 7.5 to 10,000 Kelvin. This is 10,000 Kelvin is welding gear. This is it's hotter than blast furnaces, right? Basically, this is lightning. The surface of this thing is lightning, and so it peaks in the ultraviolet even. And then F and G, this is the surface of basically the surface of the sun. K and M are also very hot, but when you get to L, T, and Y, lower than 700 Kelvin, I mean, you subtract 230, so it's a 500 degrees Celsius surface. That gets pretty close to my oven settings. These things are not warm. They're basically, they're toaster oven temperatures. So this is why they're so hard to see with the naked eye. They're not glowing in the wavelength much that you look in. They're glowing right in the near infrared. And so we're still finding these in our local neighborhood, but these have been classified or have been found for ages now. And so remember distances, think of that light of that star. It has been emitted thousands of years ago to be long gone. I keep hearing this and people keep telling third graders this, and please stop, because the stars that you can see are only tens of light years away. So instead of, oh, that star could have been gone by now, the star that you're wishing on it could have been, this died ages ago. It's like, wow, look, it was in the previous administration, that's when the light left. So the common star types, yellow dwarfs, white dwarfs, these are sort of like the common names. And of course, I've added a bunch that have absolutely nothing to do with it. There are no green and beige stars, you may notice, because again, we perceive yellow, that middle wavelength, and yellow and green, basically it's yellow. But I kind of wish there was a gray wizard. So how many of these different kinds of stars are there? Find a very big clump in the same spot, and then assume that they're all the same distance, basically if they're a nice little blob somewhere on the sky, and count how many bright ones of each type. So what we now are going to do, I'm going to set it a little darker because then you can see better. Sorry, Drew is doing family leave, so we have some. There, that's better. Sorry, I have a couple of movies. So we're going to look at this whole clump of stars, right? This is one. There's several of these that are called their clusters. And as we zoom in, we're seeing that these things are completely made out of just enormous numbers of stars. But they're all roughly at the same distance, so we don't have to worry about distance so much. There's bright ones, there's fainter ones. Okay, let's look at that in detail, right? So if I look at that in detail, this is sort of like the last bit. Slow down a little bit. So this is from the ground. You can already see that there are thousands of stars, and we're going to assume that they all started life at the same time. Wow, this is slowing down quite a bit. What we now want to do is see how many red, blue, and what kind of colors there are. And so once you get into the center, though, they're so close together, you can't see the individual stars anymore. So you have to go to something that has an even better, sharper picture of this. Yes, that means you go to space and you get a Hubble Space Telescope to take a picture of the center of this star cluster. And as you can see, it's basically all like lots of faint ones and also lots of, but not as many, brighter ones. And since they're all at the same distance, you can sort of figure out what the number of really bright ones versus the number of faint ones. So color-coded it now. You can see blue stars, you can see red stars, and lots of yellow stars, right? So first first impression is yellow stars are very common, but you have bright red and bright blue ones, but I can also see not so bright blue ones. And so suppose you actually keep looking at it like everything is orbiting everything else, so you expect this whole glom of stars. Next. Sorry, I broke up the video in a couple of. Okay, here we go. So when we start with this, we see we have the red ones, the yellow ones, and the blue ones. And so we're going to make something called a Russell diagram, also a color magnitude diagram. We've encountered this already: temperature and brightness. And since they're all at the same distance, we take the distance out of the whole equation. So we're going to order all the ones. We're going to order them by color, right? So we're moving all the blue ones to the left and all the red ones to the right, and we're ending up with a whole bunch of yellow here in the middle. And now I'm going to order with the brightest one at the top and the dimmest ones at the bottom. Organized that way, suddenly a whole bunch of structure shows up. This stuff knows about it, right? So temperature and the luminosity know about each other. And so we have something called the main sequence. They have red giants over here. They're big and the same color as the blue ones over here. And then we have blue giants over here. And all the way down here are white dwarfs. The occasional time we find a very dim, but also very blue, and therefore very hot star. So if we put everything on color and total magnitude, total absolute magnitude, so the absolute luminosity, then we get something like called the color magnitude diagram. So color on here, and absolute magnitude, so lower number, but basically brighter over here. And then we can actually see where those spectral types end up. And so the A and B stars are over here, O stars would be over here, O, B, A, F, guy, girl, kiss, me, right? So that's where all the different colors end up. So you have the big bright blue ones over here, the part of the main sequence, and then giants over here, giants, bright giants, and supergiants, and those end up having the same colors as the dwarfs over here. With me on that? Okay, so this color means temperature, right? So temperature goes from right to left. We counted that already. This is the reason that we put it that way, because basically somebody organized blue on the left and red on the right, and now temperature goes this way. So we have the main sequence. This is where we saw most of the stars, right? In our cluster, this is where the vast majority. Ooh. Okay. I have to stand exactly here, apparently, for technology to work. And so this is where the main sequence, this is where we saw most of the stars in our cluster. We didn't see these here, like the cluster's a little older, so we only saw up to here, and then we saw it basically bend over into the giants. But there are younger clusters, I'm foreshadowing here a little bit, that have a blue component. All those new brown dwarfs, they live down there. Effectively, the color goes all the way into the near infrared, and they're so faint that we typically wouldn't see them even on an and so we get O, B, A, F, G, K, M, and then L, T, and Y. Basically, they're off the chart here. And then up there, what's happening over there, right? So this was the majority, and then we saw a lot of them here. And these are red giants. We can see one, Betelgeuse, which is in Orion, like it's the red, it's his armpit. It's the red giant. That is a kind of one of these over there. That is a sort of midlife stage or end stage of life for these stars. Just to give you an idea of the sizes of these things, so here's Earth, Venus, so here's Neptune. We're going to add Saturn without the rings, so like that's Earth right there. Keep the top with like little Earth over there. This is Jupiter, and remember that little blue thing? No, the tiny blue thing there. That's the sun. Right? The sun is already dwarfing everything in the solar system. That's our sun. And then Pollux, for example, is one of one of those giants. Arcturus is another one of those giants. These things are very, very bright. Here's our sun, by the way. Keep an eye. Aldebaran is an actual star, not just a Star Wars. They ride those rival the distant stars. A new one, Antares A, another red supergiant. Our sun is, I don't know, basically under my laser dot there. And the current one is Canis Majoris, is the red hypergiant. So it's found behind the big dog. But it is the largest star found so far. It is an absolute giant of a star. So that's what these things are here. They're big, but they're cool, right? So remember that temperature goes this way. So they're bright because they're so large, not because they're so hot. The predominant reason that they're so bright is because they poofed up. They're really big stars. Then there's another one on sort of like the far side, which are called white dwarfs. Not this one, that over there, right? So this is these tiny, very dim, like 10 magnitudes below the main sequence, we find white dwarfs. And those are important. We'll talk about them when we talk about the death of stars. Literally, these are the corpses. This is what's left over after a star has done its entire lifetime, and this is a little smoldering ember that's left over. So white dwarfs were found again in a cluster like that, and we find these little blue dots scattered in between. So that's what's left over after a big star has ended. So giants are a relatively short-lived evolutionary stage, right? So you start at the main sequence, and then you go through a giant phase. You puff up, you become this big, cooler but bigger giant. And at the end are the remnants. They no longer create energy by fusion. They're no longer alive. Like we anthropomorphize everything, even in astronomy, and so we don't think of stars as alive if they don't fuse material anymore. Just to give you an idea again of scale, because you don't see the video maybe on the slides, Betelgeuse is sort of the nearby supergiant star. It has 500 solar radii, right? So this is Earth by comparison, and so the sun is, big by comparison, but the sun fits easily within Aldebaran, and then that easily fits, like the entire inner solar system fits within Betelgeuse. Betelgeuse being one of those giant stars. And so, just to give you an idea, so this is what it looks like. You get into the white dwarfs at the bottom here. This is the entirety of the main sequence, and then you get these shorter-lived stages here at the various giants, various kinds of giants. This is like what it really looks like if you look at a whole cluster of stars. I like this one as well because it's a little more artistic. So you have the main sequence, the supergiant, and the white dwarfs down here. And I like the fact that you can pick out the sun and then all the other stars that you may or may not have heard of. And we also look at this, it's like this is here's one solar mass, 1.5 times the solar mass, 6 times solar masses, 10 solar suns, 30, 60. So the further up the main sequence you get, the bigger, the more massive also these stars are. So bigger, more massive is brighter and hotter. And you can sort of think of that in physics terms because remember that it's really, really big, it's compressing the center faster, which means that it has to withstand that pressure. It has to put out energy in order to withstand the pressure. To do so, it has to fuse material. So it burns through its fuel faster in order to keep the pressure from the outer parts of that sun. It also means that there isn't a lot of convection. So more massive, you start down here with like 0.2 of the solar masses. Here's the sun as 1. And all the way to about 60. I think the biggest one we found is 150. So that's O star that has 150 solar masses. However, you can now do the back of the envelope calculation. So this is an estimate, right? You say, okay, the lifetime is the total fuel available over the rate of fuel consumption. So that's the mass over its luminosity. Because I'm using the fuel, and we'll talk about what fuel is in a minute, but it has a certain amount of fuel, and you have a certain amount of mileage, essentially, how much light you're producing. And that means, let's see, the lifetime, so you divide mass by the luminosity, and the luminosity goes as the mass to the 4. So you end up with 1 over mass to the 3rd times the 10 billion years. So you can say like, okay, got 1 solar mass divided by, oh, so 1 over the solar mass cubed, that's 1, so 10 billion years, our sun's gonna live 10 billion years. If I have 0.2 of a solar mass, for example, or 0.1, let's make it easy on myself. 0.12 cubed is 0.0001, so that's a thousandth times 10 billion years, so that's a thousandth, but you do 1 over, right? So this is a thousand times 10 billion years. That's 10 trillion years. So the lowest mass stars will not run out of fuel for the next trillion years or so. So we haven't seen any of them die. We don't know what they do. But if you're a really massive star, say 10 solar masses, you go, okay, this becomes a thousandth, so this becomes 10 million years. We find fossils here that are older than 10 million years. So those things burn in cosmic terms, they burn through their fuel like that. 100 solar masses burns through it in a couple of thousand years, length of human civilization. So some stars, the more massive they are, the short-lived they are. So for example, here you can see some of these examples, 10 to the 10, like that's 10 billion years. Sirius, 2 solar masses, that's only a billion years. Spica, that's only 100,000 years. And that's only 11 solar masses. So something like 150 solar masses lives a couple of thousand years. But meanwhile, if you go to really small, then 10 to the 12, yes, it's a trillion years. So million, billion, trillion. So this is 100, this is 10 million years, which is still a lot, but again, if you're thinking in geological terms, not so much anymore. So, longer lifetime, and then higher mass, right? Mass goes this way, lifetime goes the other. So, the way that I remember that is live fast, die young, and then, in case of stars, leave a smoldering corpse. That's the right course. So, what you see is that the higher masses, right, the ones that are further along the main sequence, are the first ones to first turn off and become a red giant, and then they die, right? So this is sort of like just before they actually completely stop burning, is they turn off and become cooler and puff up. And so I have a HR working group, so I've got an HR Russell group work. Russell work on it for the next 8 minutes. Groups. Turn the light up. Sneaky here. I make plenty, I always do that. Shortest lived. So the shortest lived ones disappear first. If you're really, really big, you also need a lot of fuel. It's sort of maybe your car's mileage. thinking I already put this video in, and I haven't. So, this is another group of stars. You can see it in the picture because this is usually when Drew saves my bacon and manages to darken the room. But now I have to do it myself, so. All right. So as you can see, the early stars, the shortest lived ones, are the first ones to turn up, the first ones to disappear. So as the time goes forward, like you go lower and lower down the main sequence, that the stars turn off. Sorry, let's see if we can do this again. So this is a Hubble Space Telescope picture of one of the nearest dwarf galaxies. You wouldn't even know that you were looking at a dwarf galaxy, except that there's a collection of stars in there. And so today we see, they turn off just after the sun, and it goes up into the giants. But right at the beginning, 1 billion years after the Big Bang, and then every time as we go along, every 10 billion years, this is sun-like stars have already gone away, and we're left with everything that's basically smaller than the sun. That's what's left on the main sequence. So that's one of the oldest stellar populations in the universe that we have observed. And so the shortest lived ones, the O stars, the first ones to disappear. So if you see an O star, you know it was made in the last million years or 10 million years or so. You see O stars, they're young because they're not anything but. So if you see dwarf stars, they can be any age because their lifetime is a trillion years. So the whole universe isn't long enough for them to actually start doing whatever they do when they stop fusing hydrogen. But up here, if you stop, then you puff up, become a red giant, essentially explode, and end up as a white dwarf, a neutron star, or a black hole. So that's foreshadowing for what happens at the end of the lifetime. But most of the lifetime is spent here on the main sequence, and then the last bits are moving through these corners. And so we think of them as alive on the main sequence, and then as they start dying, they go, the first ones move off at the highest mass. So how does the size of a star in the top left of the HR diagram compare to the star with the same luminosity at the top right of the HR diagram? Right, with the same size, the star in the top left is larger, the star at the top right is larger. There's insufficient information to determine this, right? So if I'm the stars over here versus the stars over here, they're both 10,000 solar luminosities, right? Which one of them is larger? A, they're the same size. B, the star near the top left is larger. The star near the top right is larger if there's insufficient information. Voting in 1, voting in 2, and voting in 3. I just showed you all these giants. They're all red, right? They're the same brightness because they puffed up much larger than their blue cousins. And so the top right is much larger. In order to get the same kind of luminosity, you need to blow up the star to much larger sizes. Star Rigel is about 100,000 times brighter than the sun and belongs to a spectral type called P8. The star Sirius B is about 3,000 times dimmer than the sun and also belongs to the spectral type P8. Which star has the greatest surface temperature? Rigel, Sirius B, they have the same temperature. There's insufficient information. All right, I'm going to walk around. I'm going to turn to your neighbor, and even if the two of you agree, convince them why your answer is correct. Talk to your neighbor. podium 2, podium 3. I have A and C now in the room. All right, A is where I do, the other one is at the same temperature. Okay.
Wait, which one was it?
We have, both of them are B8, right? One of them is 100 times brighter than the sun, one of them is 3,000 times dimmer than the sun. They're both at spectral type B8. So, B5, B8, that's about here. So I either have B5, B8, that's over here. So I'm either having like really, really bright, much brighter than the sun, or much dimmer than the sun. But they are the same temperature because they're the same spectral class, right? If you start spectral class, you're talking temperature. Notice temperature on the x-axis on the bottom, but also spectral type at the top. Spectral type is temperature. So if it's an M5, it has 3,000 Kelvin. If it's a B5, it's almost 20,000. If it's B8, it's close to 20,000 Kelvin. One of them is a white dwarf, and one of them is a blue B8 giant. But they're the same surface temperature. One of them is just tiny. See, so those are the two things, like how big is the star and how hot is that, right? So you can have the same spectral type, they're the same temperature, but one of them is much, much dimmer because it's basically white. Yes? Okay. Couple questions about that. So which one's hotter, B3 or an A7? So B3 or A7? B3. Which one's hotter, B0 or B9? B9, right? So the further you get in the spectral classification, the hotter it all gets, and also the brighter it ends up getting. The last thing is like, well, how many of each star? And so that's sort of the last fundamental bit, where we have stellar mass here on the x-axis and the relative number. So if I'm talking one solar mass, so the sun's here, I've got, on either end of that, I've got 50 of those. If I'm going between 2 and 10, I only got 10 of those. So for every 10 solar mass star, somewhere between 2 and 10, I only have 10 versus every 50. So for every sun, I only have 1/5 of one of these. Or basically, if I take one of these, I have 10 suns. That sounds very prodigious. So let's say for every sun, I have, for example, 200 of all the smaller stars. For 50 sun-like stars, I have 1 O star. These things are rare. And so what we call this is the initial mass function. So basically, as you get started and you make a whole bunch of stars, you typically end up making one that is 30-ish to 50-ish solar masses, right? You make one big whopper of a star. And then you make a couple of pretty big 10 solar mass-ish stars. And you make 50 of sun-like stars. And then 200 of the M dwarf, like a 10th of a solar mass kind of stars. So those things are everywhere. And also they don't die, right? So these things stick around on top of it. And as you start off, you have lots of dwarfs, lots of a reasonable amount of intermediate, and then only a few big ones. But those things are so bright that, if you can only look at something at a distance, you'll pick this guy up no matter what. It's the brightest thing around. You have to really look at it for a long time to start picking those up. So if you look for a clump of stars, that one's the first one you pick up. So this is sort of how you do that in an actual scientific plot. I literally stole this out of a scientific paper. And so we use a log. So the reason that I'm doing this is to get you used to the fact that we sometimes plot things not on a linear scale, where every step is, this is 1, 2, 3, but every step is 1, 10, 100, 1,000, right? That's what we're doing here. Log of a mass of 0, that's the sun, and the number I have here is a log of 0, which is 1. So for each sun here, I have, for half a solar mass, I already have 10 to the 10. I have 10 of those. And if I go to 0.8, it's like this is the almost a tenth of the solar mass. If I go up here, I'm talking 10 to the 2, so 100 to 200 to 300. Sorry, 100 to almost 1,000 of those. Right, so these endorse. It's unclear how many little things you get for each sun that you get here. So this is normalized on letting one solar mass means one of them. And then if you go down to 2, so that is 100 solar masses, I go down to lower than 10 to the minus 4, which means that I need 10,000 suns essentially to get one of those. That's the ratios that we're talking about. Does this make sense? Does this plot make sense to everyone? The reason that I'm doing that is that sometimes this is actually a good way to obfuscate information, because I need to, like, my masses go from 0.01 solar masses to 200, 300. So to put that all on one scale, using a logarithmic, so steps of 10, makes sense. The numbers go from, 1,000 to 10,000 to minus, like, basically from 10,000 to 10,000. So that is such a large scale that, again, a logarithmic scale makes sense. But if you go like, oh, this is a linear relation, no, it's not. It means that every step of 10 means an upscaling of 10 that way. So this is what's called the power law. And a lot of things in nature and a lot of things elsewhere are power laws. So if you look at a graph, if somebody's giving you a graph and go like, this is important, right? This is the pH of the Ohio River that goes by your property, and like here it is, and don't worry, it's only 1 off, but that's a pH is a log scale. Meaning 1 off means it's 10 times wherever it's supposed to be. And so I want you to evaluate when you are being presented with data, with information, is that a logarithmic scale or is that a linear scale? Is it a linear scale on the x-axis and the log scale on the y-axis? And what are people trying to tell me? Like, if this is a relation, fine, but that means it is a power law. It is not a linear relation. You will have to encounter that, especially if you go into science somewhere, because often the scales are such that we have to put it on a logarithmic scale. So I find this useful as an example, because this is as obfuscated as it gets, right? Yeah, sure, they put in the nice little legend up here, and actually, who did what, but you have to read it. It's like, okay, steps of 10 this way, steps of 10 that way. What does this line mean? It means that if I go one step here, it means that I'm 10 times more massive, but also 100th of a times more rare. So that's how I should read that line. This is a science class, and this is the kind of way that you present science like this. So chemistry, medicine, everybody uses logarithmic scales, and especially for stars, they're incredibly useful because I wouldn't be able to fit this on the screen otherwise. So there's a reason I'm using it, but there's also a reason for me to use it if I want to make a big change look small. Okay? It's not disingenuous. Sometimes that's the best way to do it, but I want you to realize when that is being presented to you. Cool. So that's what we do. This is the kind of numbers that you start with, and then we saw from the video like the biggest ones. These ones are also they're rare, and they're the first ones to disappear. But they're so bright that we're going to pick them up. So when we talk about galaxies, we go like, wow, that looks blue. Yeah, because you've got a few of those hanging around. But they're not going to be there for long. So anytime that you see no star, that means it's in the last million years, somebody's been making new stars there. So there's a new star formation, and you see O and B stars because they don't hang around that long. All right, so how many of each star? That's the kind of numbers that's what that line means, and then you expect like just a few of those. So I think, we sort of got it in the right time. If anybody has, so this is why I left a little extra time, questions about the midterm, or you would like to make the following use. If you suspect that you've got a couple of multiple choice questions wrong, come get it. Make sure that you've got you explain to me why you took the wrong question, and explain to me what the right question answer is, and then you can still get half the points back. So that doesn't need to be your final grade on it, okay? But I do want to